The two-body problem that we just described is actually a complex one. Instead of trying to solve it directly, let us try to find some properties about its motion. Consider the motion of a satellite around the Earth. We begin by dot multiplying the equation of motion by the velocity v of a satellite. Remember that v is the time derivative of the position, so we may write this expression like this. And after integration, we get this other expression. This equation states that the sum of the kinetic energy, over here, and the gravitational potential energy, this other one, is conserved over time. Therefore, we say that the system is conservative, and we call this equation the conservation of mechanical energy, E, of the satellite. Observe that with this definition, the kinetic energy is always greater or equal to 0, while the potential energy is negative and only becomes 0 at infinity. Indeed, we can see that the mechanical energy is constant in the following simulation. As the satellite moves farther away from the Earth, gravity slows it down and therefore loses kinetic energy. On the other hand, at the same time, it gains potential energy in the same amount. Therefore, during motion, the satellite trades kinetic energy and potential energy, keeping the sum of the two of them constant. Finally, we can also see that a satellite reaches zero velocity when the potential energy equals the mechanical energy. This defines the maximum distance r that the satellite could possibly move away from the Earth. We see that only when E is equal to 0 or larger, r can possibly go to infinity. As we shall see later, this is the case of a parabolic orbit and a hyperbolic orbit, respectively. On the other hand, when the energy E is negative, it remains bounded in an elliptic orbit around the Earth.